dear learners, for this course on turbo machines. In this module 2, we were discussing about energy transferring turbo machines and general analysis of turbo machines. So far, we have discussed some very important proofs regarding power absorbing turbo machines, that is pumps or compressors. We have discussed about radial outward flow turbo machine and axial flow power absorbing turbo machine. So moving for the final theory concept of this module 2, and one of the most important theoretical concept, that is theoretical head capacity relationship for centrifugal pump or compressor. Before moving to derive the theoretical head capacity relationship for centrifugal pump or compressor, one should know the different velocity triangles for centrifugal pump. First, let us discuss the velocity triangle for centrifugal pump, and later we will derive the theoretical head capacity relationship and discuss what is the effect of blade discharge angle on head for a constant flow rate. Let us discuss the velocity triangles for centrifugal pump first. Coming for velocity triangle of a centrifugal pump, for a centrifugal pumps there will not be any drill at inlet. So therefore, always for a centrifugal pump, alpha 1 is equal to 90 degrees and Vu1 is equal to 0. Whenever you see the word centrifugal, always you should take alpha 1 as 90 degree and Vu1 is equal to 0. This is because of the reason for centrifugal pumps there will not be any brill at inlet. So therefore, inlet velocity triangle is always constant. That is, we have the inlet velocity triangle as a right angle triangle with Vf1 is equal to V1, alpha 1 is always 90 degrees and Vu1 is equal to 0 because no brill at inlet for centrifugal pump. This is Vu1, we have blade angle beta 1 and fluid is moving upward, we have Vr1. Now, depending on the blade, whether it is curved towards the direction of rotation or curved backward towards the direction of rotation, or it will be radial. So based on that, we have three different types of blading arrangements for centrifugal pump. One is forward curved wing, second one is backward curved wing, and third one is radial wing. Let us discuss one by one. First one is backward curved wing. So if I have backward curved wing, that is, if the blade is curved opposite to the direction of rotation, then we term it as backward curved wing. For backward curved wing, if I draw the velocity triangle, I will get the velocity triangle at exit as like this. This will be Vr2 and this is the direction of U. This is Vf2 and this will be V2. So always V2 is the reference. V2 to Vf2 will be Vu2 and V2 to Vr2 will be U2. So this is when beta is less than 90 degree, that is beta 2 is less than 90 degree, and this is alpha. So this is called as backward curved wing, in which beta 2 is less than 90 degrees. Coming for the second one, that is radial wings. If I have radial wings, the inlet velocity triangle is constant. As I said, we have right angle triangle at inlet, no change in inlet velocity triangle, that is always 0. Now for radial wings, the blade is radial, we have a radial blade move with velocity u. The outlet velocity triangle for this will be a right angle triangle. Since blade is radial, we have Bf2 is equal to Br2. So therefore, beta 2 is 90 degrees. Keep this in mind. Beta 2 is 90 degrees, and we have Bu2 is equal to U2 here for this case, and we have left out with alpha 2 and P2. So blade is moving in this direction. This is termed as radial way. That is beta 2 is equal to 90 degrees. The third type of blading arrangement is forward curved wing, where in which the blades are curved towards the direction of rotation. The inlet velocity triangle is always same, it is constant, no winglet inlet, so no change. We have Vf1 is equal to V1, alpha 1 is 90 degrees, and Vu1 is always 0 for centrifugal pump. We have only checked with U1. Here I have beta 1, what is moving upward. We have Vr1. So it is curved towards the direction of rotation, like this. Forward curved wings. This is U. So for forward curved wings, we have the velocity triangle like this. So this will be Vr2, Vf2 and V2. We have beta greater than 90. This is beta 2 greater than 90 degree. This is alpha 2. So absolute is a reference. Absolute relative is U 2 and absolute flow is Vu2. So if you observe here, the blade is curved in the opposite direction to the direction of rotation. Blades are radial. Blade is curved towards the direction of rotation. This is third category is known as forward curved wing. Forward curved wing. That is beta 2 is greater than 90 degrees. So these are the three different velocity triangles for centrifugal pump, which one should know. Separately, this can also be asked. Sketch different velocity triangles for centrifugal pump. That is for backward curved wings, radial wings, and forward curved wings. For all these, the inlet velocity triangle is constant. That is no inlet entry. Only the exit velocity triangle varies. Beta 2 less than 90, beta 2 is equal to 90, and beta 2 greater than 90 degrees. With this knowledge, we always consider backward curved wing default. So backward curved wings are advantageous, and if you observe for backward curved wing, once we derive, we can come to know that as head decreases, the discharge keep on increases. So therefore, we always prefer backward curved wings. By default, if nothing is stated regarding the wings for centrifugal pump problems, always you should start with backward curved wings. Mark it as important. This is a default velocity triangle for us. Now, let us derive the theoretical and capacity relationship based on these velocity triangles. What we have coming for theoretical and capacity relationship, we want head form. So we know that for power absorbed in turbo machines. Euler's equation of energy transfer is nothing but work done per kg is given by VU2 U2 minus VU1 U1 by GC. This you know that. So if you solve this, you get the answer in terms of joules per kg. But if you want it in head form, so the head form of Euler's equation of energy transfer is obtained by dividing actual energy transfer by acceleration due to gravity, that is 9.81. So head form is obtained by dividing energy transfer by acceleration due to gravity. So therefore head form of Euler's equation of energy transfer is given by du2 u2 minus du1 u1 by g into gc, where g is 9.81 meter per second square, whereas gc is 1 kg meter per Newton second square. This we have discussed in the lecture 1 itself. So therefore I will substitute the value of GC as 1, and for centrifugal pump, if you observe, VU1 is always 0. So therefore the head form will be H is equal to VU2 U2 by G, that is 9.81. I substituted GC as 1 because GC is 1 and VU1 is 0. Now again I can write VU2 as I said, from backward curved veins default, from backward curved vein velocity triangle, VU2 can be written as U2 minus VF2 cot beta 2. So therefore the head form will become U2 into VU2 is U2 minus VF2 cot beta 2 by G. So further simplification leads us H is equal to U2 square by G minus U2 VF2 cot beta 2 by G. So we obtained the head form. Now I should introduce capacity, that is discharge. So we already know that discharge Q is equal to area of flow into velocity of flow, where flow area is nothing but pi dV. So diameter into breadth. So therefore I can write EF2 as discharge divided by outer flow area, that is pi d2 b2, outer external diameter and breadth of the width of the veins at outlet. So introducing that to this equation, I will get head H is equal to U2 square by G minus U2 into Q. It can be written, VF2 can be written as Q divided by AF2G into cot beta 2. So this I can write it as H is equal to K1 minus K2 into Q. So this is theoretical head capacity relationship. U2 Q by AF2 G. Right. So now if you observe, for beta 2 less than 90 degrees, cot beta 2 is negative. So therefore, cot beta 2 is positive. So first case is backward curved vanes. For backward curved vanes for beta 2 less than 90 degrees, cot beta 2 is positive. So therefore H decreases as Q increases. Next, coming for radial vanes. For beta 2 is equal to 90 degrees, cot beta 2 is 0. Therefore H is constant. K2 term will become 0, H is equal to K1, where K1 is U2 square by G. For forward curved vanes, that is beta 2 greater than 90 degrees, cot beta 2 is negative. Therefore H increases with increasing Q. So based on this analysis, if I plot the graph, I will get the head versus discharge as this is head H in meters versus we have discharge Q in meter cube per second. So here we have H is constant, that is U2 square by G, which is termed as shut-off head. This is for beta 2 is equal to 90 degrees. We have neutral. For beta 2 less than 90 degrees, we have decreasing observation. For beta 2 greater than 90 degrees, cot beta 2 is negative, therefore H will increase with Q. So this is termed as shut-off head. This is termed as shut-off head. The magnitude of shut-off head is known to us. The magnitude of shut-off head is K1, which is nothing but U2 square by G. The magnitude of shut-off head is U2 square by G. So this is the theoretical head capacity relationship. If I use backward curved vanes, as head decreases, discharge will increases, or increase in discharge will decreases the head. If I use radial vanes, I will get shut-off head, that is head remains constant. If I use forward curved vanes, I will get increasing discharge will cause increasing head. So this is about the theoretical head capacity relationship. A very important one to be known by a mechanical engineer. With this, we have completed all the theoretical concepts of module 2. From next lecture, we will be heading to conduct analysis of power absorbing turbo machines. That is, we are going to solve problems on fans, blowers, compressors, etc. And since we have the centrifugal pump itself as a module, that is module 5 is purely dedicated for centrifugal pumps and compressors. I won't take problems on centrifugal pumps in this module. We will discuss other power absorbing turbo machines such as fan, blower,